Okay, so I am Adam Day. I work for Sage Publishing. We're a large academic publisher. We recently worked with OpenCredo, with Ebru Cucen at OpenCredo, on a project around detecting research fraud, but also around sort of building the kind of data infrastructure that we need to do this in the future. Just want to make a quick shout out to our colleagues, Farron and Seb at OpenCredo, as well as Helen King, who I work with at Sage. So things I'd like you to kind of remember after this presentation. The first one just being that graph analytics have proven themselves to be quite effective in fraud detection in the past. Doing it well does require carefully built data structures with well-curated data, such as OpenAlex, which is a new data set that's just been built recently, covering a lot of the research literature. And what we found in this project was that we can detect unusual co-authorships, right? It's, when two people are working on the same paper, and it's unusual, something's unusual about it. So we can do that with machine learning. That works quite well. But actually, there's just a simple rule here, which is that when someone writes their first paper, it's really unusual that they write their first paper co-authoring with somebody at a different institution. Okay? This is a strange thing, and it's worth coming from an editorial background. If you're editing a science journal, this is something to look out for. Okay, so this was a project I did last year. So these little notes here, these are referee accounts in a peer review system, okay? And if you see two nodes that are joined together like this, what this means is that, cheers. What this means when they're joined together is just that at some point, these two referee accounts have written reports in the peer review system that are identical, okay, or highly similar. And sometimes you just get like a couple like this, and it turns out this can be quite innocent, doesn't really match that much. But when you see a big lot of referees all using the same referee reports, that suggests something is up, and it definitely is. This turns out to be the work of a paper mill. That was an organization that was trying to manipulate the peer review process. Yeah, the real value of using graph analytics comes when you start connecting this to other stuff, because this is like leads, right? This tells us where something dodgy has happened. But sometimes you find that authors recommend these referees. You think, okay, well, the author is probably in on that. Then you find that the authors have co-authors, and they've got past co-authors, and they've got past papers they've written. All of this is now suspect and worth looking into. I'll explain a bit about what paper mills are, because not everyone is familiar with that concept. So this right here, this is a very, very naughty man, okay? And what he does is he goes around and he looks for somebody who can write a fake paper, right? So this person writes a fake paper for him, gets some money, and then he goes and has another look around. He says, well, maybe I can find somebody who wants to be an author, okay? Maybe this person has like a career incentive to become an author, right? They have to publish a paper in order to graduate or in order to become a doctor, something like that. And they might not have the resources to do it either. They might not have the money, they might not have the English language writing skills, things like that. So they just pay some money to the agent. The agent puts their name on the fake paper, and they send it off to a journal to get published. Now you might think that, well, we have a peer review system, right? And the peer review system is there to catch these cases. But as you can see, there's an effort to manipulate the peer review system. And also the peer review system fundamentally is based on trust. It's based on being able to assume that the papers coming in are an author's honest work. They might be flawed scientifically. That's what peer review is meant to check, not whether they're completely fake. Just 2 days ago, this graph came out in an article in the BMJ. And this shows the rate of retractions related to paper mills specifically, and when these articles were published, okay? So it looks like it's going down, right? It looks like it's going away, it's great. Unfortunately, the retractions always lag the time of publication. Really, we should expect to see this continue to go up. Also, retractions, this is a bit of a cliche when talking about this stuff, but they are the tip of the iceberg. They show you a small percentage of the actual paper mills that are out there that haven't been detected. So this is a really serious problem. It's massive, and it's just now something that people are trying to take note of. So you might think, okay, well, maybe we can find some AI method to detect all of these. AI generally isn't really helping. There are some AI-based tools to detect paper mills already. I've made some of them myself, and they don't solve the problem on their own, but they do help a little bit. But there's already a huge number of examples of cases where papers were written with the help of GPT-2, and these were detectable and very large numbers of papers. Interestingly, there aren't any examples of fake papers that have been generated with GPT-3 or later models, which is strange, right? But probably it just means that it's reached a point where we can't detect it anymore, at least not easily. You're going to make some fake scientific images. You can use Stable Diffusion. It takes a few minutes. You just take the caption off an image, shove it in, it'll give you a fake scientific image. That's always been a good way to catch them, is image fakery. But that's probably going to go away. Meta, a couple of weeks ago, I think now, they released a model specifically for generating scientific text, which, given the above context, might not have been a great idea, and it was swiftly pulled. A little article about it here, but basically a lot of scientists complained that paper mills might use it, and also there's a few other reasons why that was maybe a bit of a premature launch. Okay, so you remember that agent, right, who's in our little graph? He's looking for people who want to buy his fake papers, right? This was a website called Retraction Watch. Did this story back in 2019 about just such an agent that was actually advertising all of the fake papers they had. Actually, the papers might have even been real. We don't know. We just know that there were papers on this website where authorship was for sale. Might seem a bit daft to do that, because what happened was Anna Abokina, she's a researcher in Berlin. She went through that website. It was all in Russian, but she translated it into English, searched for all of those papers, found out where they all got published, figured out who all the authors were who had paid to get their name on those papers. And well, this is really great for us because it means we now have this kind of ground truth data set, right? Which is a really rare thing because usually you can't find enough to train models, right? But now we have this data set where we know that the authorships were brokered, okay? And so what we can do is we can get another data set of related papers, so just similar papers, and then we can compare the two, and we can start to see, well, can we actually tell the difference? So, these are our questions. Can we take that publicly available data, model the co-authorships, and can we tell the difference? So I'll now pass you over to Ebru, who will tell you about the data engineering part of this.
Thank you.
OpenAlex dataset, which is it's free, publicly available. Hundreds of millions of data entities we have.
It was inspired by the ancient library of Alexandria, and Microsoft Open Access, the academic graph team actually is supporting this. It was launched officially on September 2022, a couple of months back. What we have done is started the work April time, which means that it wasn't the production-ready data set we started working. And it's a bit brave because we haven't had the official kind of data set, but the team is very supportive and they did updates regularly. So we have the new revisions and the new updates of the data set. It's about 1.7 terabyte of data we downloaded as a snapshot. It's available on AWS S3. You can access through the web browser or the API for the full text search or any kind of sources that you are using. If you are using Snowflake, you can browse from the marketplace. It consists of the authors, works, concepts, venues, and the institutions. They are the core entities they publish. If we step back, look at how the data engineering world for the data science platforms, how we prepare them. Google tells it the high interest credit card of technical debt because it takes too much time to publish the machine learning algorithms. Joe Rayson, who is actually, they call themselves as recovering data scientists because it takes so much time and effort to get the machine learning models published. They actually worked on the, they have a book, Fundamentals of Data Engineering, and this is their data science hierarchy of needs. It looks very trivial. Like, if you want to go to the Everest, you have the steps. You need to collect the data from multiple sources. You need to store them in structured or unstructured via reliable data flows. You do explore and do the transformations required. Then you need to aggregate to do the metrics and the labeling process. You will train the data and the optimizations, which will give you the A/B testing or kind of validation of how good you are doing. And then you are there at the top of the nirvana. It is like the Hercules story of 12 tasks. I don't know, as you may know, Hera, his stepmother, punished him. She hated him, actually. And Hercules killed his family. And Hercules went to Oracle of Delphi, asked for penance. He was given the task of 12 items to kill the lion, to kill the boar, and so on. At the end of the story, he was made immortal and he was forgiven all his crimes. His stepmother, Hera, apologized and gave her daughter to marry him. So it's a very happy ending that it ends and finish. But in the data engineering world, it doesn't happen. It's not your model publish or the go-live version of your code is the same as the software. It doesn't finish there. It doesn't finalize. It's a live system. Always there's a new source of data. There's new transformations required, new optimizations needed. It reminds me more of doing the Sisyphus, that he's been punished in the underworld to do the push this rock. Whenever it goes down. So it's more of going forward to step backward to understand what's going on and pushing it continuously. Albert Camus suggested that actually if you accept this, you will be happy. So maybe it's the state of the mind that we just need to accept this is what is happening and we just need to keep it going. In our project, we did start with the modeling data to understand what's happening. We did extract the data from the S3 bucket to GCP and load it to the graph database, done some transformations to make it more feasible for the learnings, and continues to change this on and off. So it's an ongoing process. One of the examples is, for example, the concepts. This is the API result for the concept entity. It has about 400 properties, not all of them we need. And given the small budget we have, we didn't want to kind of spend all the money. The concepts, they have all the translations for the concept keys. This is a computer science keyword, for example. We decided that just English is enough. The linking between the works and the concepts has been done by OpenAlex, and we can rely on those links. So we ignore them and just pick the top 12 properties that we needed. Then we looked at the authors, kind of, the data was a bit half full. For example, if we look at org IDs, for example, some people in the publishing world apparently rely on that, but some of the data sets had 96% emptiness, which means that we couldn't link them. Twitter ID is the most desperate one, it looks like. There were only 3 in the subset of the data. But there are also other projects going on that they do just do the Twitter mapping. So it's kind of another area that you can create more links, but in the OpenAlex dataset, we couldn't use that. So we had to rely on what we know as the OpenAlex IDs as they publish. We ended up with author. A work has an author published. A work can be related to itself. It may reference to another article or published work, and each work have concepts, multiple concepts. Concepts may have multiple levels, like the ancestor relationship between 0 and 5, or they can be related with each other, which gives us the connections actually to explore. Then the kind of the ingestion process, after we define, okay, these are the things we are going to focus, these are the properties we are going to ingest for our first pipeline. It's the Airflow kind of pipeline we set up. Whenever we needed extra requirements, extra features, we just had to add to the existing pipeline. Pipeline as code helps, kind of just to get there. And this is one example of the co-authorship. We can make the easy query in terms of give me the number of them, give me for each work the authors had worked on this together. It just gives you kind of some representation. Graph does help. But we need more. We need to understand how these two entities, two authors, are related. And our fraud detection is relying on the trust between them or the peer review. As Adam suggested, how reliable are they? How we can trust them? One model question we had, maybe we should look at how many times they did work before. So that would tell us the relationship between them, and the strength of them will identify if this is a good identifier of misconduct or not. Another way it helps is actually creating a subgraph. This is just creating those relationships and creating the submodel. It's more of creating a smaller size of the database we have, because the data we ingested was about 1.7 billion relationships and 400 million authors. So it was quite big, to be fair, and we had to do some subgraphs in terms of be able to run the queries timely without the penalty of the performance of the size or the computing power required. So this is a subgraph which helps. We can export it and we can use in another database in a sense. We added more labels, kind of, this is the label property graph we use Neo4J, and kind of it does help you to identify and need labels as you need. The flexibility of not having a schema or schema on write. You can have as many labels as you have, as you can, and this is one example where we had the concepts, they are all concepts, there is no identifiers, it's the computer science related concepts we have, but if we run the kind of just a couple of lines of adding labels, for 65,000 concepts we had, if we can identify level 0 as being the blue ones, the yellow ones are the level 1, the internet privacy, and all the level 2 are the subcategories of that, which makes it easy to write the queries, to understand, to kind of picture what we are doing with the relationships and how the concepts are related to each other. So our theory was we will do similarity, the similarity of two authors. This is for a published work. If we have two authors, A and B, what they are going to work on, which type of work they have done before, and what type of concepts were they related to each other. Similarity is one of the ways that for machine learning algorithms you can identify how related they are. There are multiple ways of doing this, and without the graph or even with the graph, the most simple way of identifying them in X, Y axis in space, where you can identify the distance between them. So if two objects are close to each other, you think they are similar. For the authors to be able to identify which author is related to which one or how close they are in space, Jacquard similarity is one of the categorical calculations where you can say, okay, how many concepts do they share, or how many interests do they share? And then you can find out of the union, kind of how many of them are shared. This example, for example, gives 6 concepts, and none of them has been shared, which means that possibly those two authors have nothing in common. And we can do sub-levels as well. It doesn't have to be this is the first level. We can go to all these work, reference articles, and what are their concepts as well. So it's quite extensible approach to identify the relationships. And one kind of Igor and Simon are two entities here, the orange ones, that we can identify how many concepts they have shared. All the kind of yellow and orange. The reddish more ones are the work they have published. You can see the kind of one on the right-hand side has more items, and they are not have so many things in common related to other things. Lessons learned, exploring API is great. Working on small data set help us multiple iterations of the data. Working as a product team, kind of data product team helped us. We could change the data as quickly as we wanted. We could change the model rapidly and scaling the infrastructure. We used the GCP's maximum kind of settings, and it was about 20 minutes. It was about 20 pounds for the machine that we paid for ingesting a whole 1.7 billion of nodes and 400 million orders. It took just 2 hours.
Okay, so as Ebru has said, the data engineering part of this is really hard. Fortunately, the data analysis part is, as a consequence, quite straightforward. So just to sort of say what it was we're doing here. So remember, we've got an author, we've got another author, right? And both of these authors appear in the author list on one research paper, okay? And we're calling that a co-authorship, right? So this is the entity that we're interested in, is this co-authorship. And a couple of important things. First of all, we've got a bunch of co-authorships. We've got co-authorships on these suspect papers, that ground truth data set where we know they're dodgy. And we've got another set which are co-authorships on similar papers, right? Which we assume aren't dodgy. Then there's another piece of filtering that we did, which is quite important, which is that we limited this to cases where co-authors were at different institutions. And the reason for that is simply because if you look at this set of brokered authorships and you know that these were sold, it seems like if you would never need to broker an authorship to someone at the same institution that you're at, okay? So those ones seem less likely to be brokered. They're probably papers that were written by 2 or more people, and then they were submitted to this broker so that they could make some money off them. Okay, so how can we describe this? Well, for one thing, we could just look at how many papers has this author published. Okay, maybe they've published 1 paper before. Okay, before this co-authorship. Maybe this author has published 3. Okay, so we can say that the minimum number of works that this co-authorship has published is 1, and the maximum is 3. Okay, it could be the same number, but usually they're different numbers. And so we've got a little table of data here. We can say this co-authorship has a min works of 1, max works of 3. That's simple. But what about, we want to know if they've authored similar stuff before, right? Have they done related kind of work? So whenever you write a research paper, you put a load of references at the end. So you might find that the works they've done in the past have referenced the same paper, okay? And maybe there's 4 references in total, okay? And one of them is shared. Well, we call that a bibliographic coupling of 1/4, which is 0.25, okay? So this gives us just a few pieces of information about which describe this co-authorship. And then we have this final column, which is what we're trying to predict. So we have in this case, it could be a suspect articles. This could be from our set of known dodgy brokered co-authorships. And then we have, a bunch of other ones which are maybe not suspect. And so if you've done sort of data science 101 kind of stuff, this is a really simple machine learning problem at this point. And just to show you what we kind of found, well, first of all, that minworks figure, it turns out that usually there is a co-author in these dodgy co-authorships who has not published anything before, okay? And that's quite rare when we see people co-authoring with different institutions. Usually they're a bit more experienced by that point. This is quite nice because it actually gives people who work in peer review and editorial functions just a simple rule that they can use. Weirdly, there was also a difference between the MaxWorks distributions. And I think that's just because, I mean, it makes sense now that I think about it. People who sell co-authorships on their papers aren't particularly well established. If you are well established, you don't have to do that. So maybe it does make sense. And you just graph this out. You can see, you know, the orange suspect stuff, it's all down here. And the blue non-suspect stuff is all up here. So there's really two quite simple metrics that you can use, and already you're starting to see differences in the groups. That bibliographic coupling metric, huge difference again. This actually autocorrelates with that min-works metric, so it's not like quite as stark as it looks here, but even if you take away that autocorrelation, you still have quite a good difference here. And this is quite nice because this, if somebody's always looking for this, and someone has the job of having to broker fake papers to people, this check means that the only way they can do that without getting noticed is that they find two individuals who have also published lots of papers in the past that cite the same other papers, okay? Very unlikely that they'd be able to do that. Usually we can't talk about all the things that we do to find paper mills because we don't want them to find out. But this one, really not a lot that can be done about it. So machine learning works well on this. It's, as I said, a pretty good data set for it. However, that simple rule I said at the start is just as good, almost. So it's, all you're looking for is you just say, if someone's writing their first paper, they're co-authoring with someone at a different institution, that's weird, look into it. It's good advice to people running peer review systems. To build a really good model that we could use, we could apply generally, would require a lot more data, probably some more features as well, a lot more testing. So in summary, we found that graph analytics are a good approach to identifying organized misconduct, both in this project and in others. To do it well, you need to have graph data structures, such as a knowledge graph built on well-curated data. OpenAlex is a good data set for this. And finally, we found that we could identify these unusual co-authorships. And that can be done with machine learning, but actually it turns out that we have this simple rule that works almost as well. Thank you very much.